All right, so now we have another influential figure in the analog gravity community, which is Ted Jacobson from the University of Maryland, who is going to talk about phonons in an expanding Bose-Einstein condensate. Go ahead, Ted.
Okay, thank you for hosting this meeting. And thank you, Jacopo, for that beautiful talk and comments about Renault. In order not to get flummoxed, I actually wrote a few things that I wanted to say very briefly about Renault, but you've covered actually the spirit of everything I would say. I just want to acknowledge the huge gap that I feel not having Renault in this workshop and in our field and in my life going forward. I met him 25 years ago when Steve Corley and I visited Renault and his colleagues in Brussels. We were both working on understanding the dispersive Hawking effect that Bill Unruh had just derived using a numerical simulation. And we and Renault were both approaching it from a mode analysis viewpoint. That kicked off a close relationship as friends and as colleagues. I shared many wonderful times with him and I learned much physics from him. I was still learning and looking forward to learning more physics from Renault. And I deeply regret that now there's a lot he won't be able to teach me. He made a huge impact on the field, as Jacopo is just kind of summarizing. But for those of you that might not know him, I just want to mention that his interests and his insights were even much broader than analog gravity. They spanned from quantum gravity, the problem of time, quantum cosmology, the back reaction to Hawking radiation, and to the consequences for black holes and cosmology of hypothetical dispersion and dissipation of quantum fields, as well as what's most closely related to this workshop, which is detailed understanding of both classical and quantum mechanics underlying laboratory experiments of analog gravity. And we will miss him terribly in this field, and I'll miss him terribly as a friend. My talk is actually very, very simplistic compared to what we just heard from Jacopo. So I guess I apologize for that, but on the other hand, maybe it's pleasant to hear something simple sometimes. So I'll talk about an aspect of this experiment. So can you see the full screen now and display?
Yeah.
Good.
Yeah,
so I'm going to talk about an aspect of the experiment that was described in this paper done in the lab of Gretchen Campbell. The lead experimenter was Steve Eckel, who was a postdoc at the time. He's now a NIST employee. And what I'll be speaking about is actually I've been looking at in collaboration with Steve. Ian Spielman was also involved in that experiment, as I guess he spoke this morning while I was asleep in Pacific time. Okay, so specifically I want to focus on the phonons, but just before getting to that, just to sketch very briefly why BECs are such a window into analog gravity. The phonons are the Nambu-Goldstone bosons of spontaneously broken phase symmetry of the many-body state, a very simple fact that a wave function in quantum mechanics can be changed by a constant phase without changing any physics. And the space-time dependent change of the phase around a background condensate is a phonon, and that's an example of a Nambu-Goldstone boson, a very general phenomenon in field theory. And these things are, because the condensate is a quantum system of atoms, let's say ideally at zero temperature, maybe near zero, the collective degree of freedom that is these Nambu-Goldstone bosons is a quantum field. And when this happens with a background condensate that's space and or time dependent, like a black hole configuration or let's say an expanding ring, the phonons are propagating on an effective curved space-time geometry, which is determined, the geometry being determined by just a couple of intrinsic parameters of the condensate, the local speed of sound and the local flow velocity. And if in general, even the S-wave scattering length of the atoms could depend on space and time, in which case that also goes into determining what the geometry is. So this analogy can be used, as we just heard from Jacopo, and I guess others before I woke up, classical and quantum field theory in curved spacetimes, including Hawking radiation and cosmological particle creation. In the case of Hawking radiation, we have the beautiful experiments of Jeff Steinhauer already. In the case of cosmological particle creation, as far as I know, no experiment yet really exhibits that sort of particle creation. Although approaching it was an experiment, I guess, led by Chris Westbrook. So the theory of these phenomena in BECs is well developed. The ring experiment had sodium atoms in an optical dipole trap, and the ring potential was created by something I'd never heard of before, an imaging digital micromirror device that can be programmed to produce a space and time dependent potential that's imaged into the condensate. So by using this, it's possible to create a ring-shaped condensate. In this case, it had a radius between 10 and 45 microns, depending on the configuration, expanded at various supersonic speeds, and the potential had roughly this form: a quadratic term and a quartic term. There were enough atoms in the condensate so that the confinement and the shape and size of the condensate was dominated by this quartic term in the experiment. So the things that were observed in this experiment were basically classical sort of Bose-Einstein condensate hydrodynamic phenomena. So it's not, although something like it in the future, I think, could be used to observe quantum phenomena like phonon creation and correlation of quantum fluctuations of the phonon field at different points, in close analogy with cosmological structure formation from quantum fluctuations. So to observe phonon redshifting, the phonon is imprinted on the condensate initially before the ring is expanded, and then the ring is expanded with the phonon propagating on it, and the phonon frequency redshifts, the wavelength stretches, of course. Hubble friction was observed, as I'll show you, and that's the main focus of my talk, actually, is to just understand how to properly calculate what Hubble friction should be expected. Whoops. But then very complicated nonlinear phenomena were also observed when the homogeneous sloshing mode of the ring decayed by a snake instability of dark solitons that form into vortex dipole pairs, which lead to a turbulent state. This is a very interesting aspect of the experiment, but I won't be going into it in this talk. I'll just focus on these linear phenomena. So here's a picture of the experimental imaging and theoretical simulations of the experiment. Here's a phonon with 2 maxima and 2 minima, so an M equals 2 phonon mode around the ring, imprinted initially, and then the ring is expanded. And in these latter 2 boxes, the density scale is multiplied by 10 so that you can see it. It's a very complicated looking structure here. That's because the nonlinear instability has set in by this point. But quite interestingly, the original phonon still modulates the density of the condensate at this time, on top of that complicated background with short distance structure. And this is actually directly analogous to how it works in cosmology, where reheating after inflation produces, say, a thermal state with lots of short distance structure on the thermal scale. But modulating that excited state at longer wavelengths is phonon. It's primordial Mukhanov mode that was created by a parametric amplification of vacuum fluctuations. Whereas here, of course, it's a mode that was imprinted on the condensate. It's a coherent state. So how does that mode evolve? Well, it's oscillating. Here are four cases of the expansion. These two by a factor of 4.1 in the radius, these two 1.9, and an m=1 mode and an m=2 mode. The gray, so this is time horizontally and the mode amplitude or the density variation amplitude vertically. The grayed region is the time interval during which the ring is expanded. So there's an oscillating mode, and actually it is somewhat damped, probably because of Landau damping. But then it's severely damped as a result of the expansion. And a lot of this is actually just coming from the adiabatic invariant that's conserved. It's like changing the spring constant of a spring changes the amplitude. And you can actually account for a good portion of this that way. But part of the change in amplitude comes from Hubble friction. And so what I'm after in the rest of this talk is explaining how that Hubble friction comes about and how to calculate it in a setting like this, for example. So to get more specific about the curved spacetime analogy, we can describe the condensate wave function or the expectation value of the many-body operator by a complex wave function, which has a phase phi and an amplitude square root of n. N is the density, local density. And we can expand n and phi around background values, n naught, phi naught, and then neglecting the so-called quantum potential, which is a good approximation when the relevant wavelengths are long compared to the healing length of the condensate. One can show that this phase perturbation satisfies this second order partial differential equation, which looks exactly like the wave equation in a curved spacetime with a metric g. The metric, or the line element that the metric defines, is written here in terms of the laboratory time increment t and the spatial coordinate increments dxi, the local velocity vi of the condensate, and the local speed of sound c naught. So in our situation of the ring, we basically are interested in an azimuthal phonon, and so it's natural to try to reduce the problem to a one-dimensional wave equation, the one spatial dimension being the angular dimension. Not much is happening in the transverse dimension. So if we just assume that the phase is independent of the transverse coordinates on the ring, the transverse pieces of this equation just go to 0. Beware, there should be a beware sign here because there's something wrong with what I just said. And we can focus our attention just on the two-dimensional effective metric. Now, the problem with that is actually that the speed of sound that appears in that does depend on the transverse position, because in fact, when the speed of sound goes like the square root of the density of the condensate, which goes to 0 at the edge of the ring. So it's highly dependent on the transverse position. But we'd like to derive an effective equation that is just depending on the angular direction. So what are we supposed to do with this transverse dependence of the speed of sound? Well, what we did in our paper was we used the transverse average speed of sound. And then doing that, we derive a simple mode equation by just the reduction of that equation I showed you earlier. And basically, because of this factor of r, the radius of the ring here, a time derivative of r appears, and we pick up this r dot over r times the time derivative of the mode amplitude. And that's the Hubble friction term. We also have a frequency that's scaling with radius in a particular way, because the speed of sound is also scaling and the r in the denominator is. So we predicted this and compared it to the observed damping. And it was difficult to get a very good comparison clear because there are too many variables and the data was too noisy. But still a best fit could be done to the effective coefficient, if we were testing what should be the coefficient of the r dot over r term. That's our Hubble friction coefficient. And then by taking all the different runs and varying all the different parameters we could vary about the characterizing the modes and the intrinsic physics of the system, finding the chi-squared fit for this coefficient gamma h, you can see that the best chi-squared fit is this green curve, which has a gamma h of 0.55, not 1. 1 was, remember, what we predicted. On the other hand, it's not a very good chi-squared. It's 1.8 per degree of freedom. And also the difference between the gamma h equals 0.1 and the other ones is a very small difference. So unless we're just sort of lucky in capturing statistically the correct gamma by this optimizing this fit, we can't take this very seriously. So we considered this at the end of the paper a kind of indication or a hint. Some kind of Hubble friction is there, but we couldn't confirm that it was 1. Well, much to our surprise, a paper came along which showed that we had done this calculation really wrong, and that the correct prediction for gamma h was, in our setting, was much more like not 1, but 4/7, which is about 0.57, which is extremely close to the best fit that we had there of 0.55. So I wanted to understand what's going on. This is a paper by Gomez-Llorente and Plata from Tenerife. I've never met them in person. And they did a rather complete analysis of the ring-shaped expanding condensate, both how its shape scales with the radius of the ring and how linear perturbations propagate on the background. But their way of analyzing this is quite different from this analog gravity sort of viewpoint, and it really wasn't clear, even though it was clear from their paper that they had done a correct analysis. It wasn't clear to me what we had done wrong. So I wanted to just briefly tell you in the rest of the time what we did wrong and how to do it right, keeping the geometric sort of picture in mind. And what I'm telling you will appear hopefully soon in a paper with Steve that covers a lot of other ground on the evolution of fluctuations on a time and space dependent condensate. So as I said earlier, what we did to deal with the position dependence of the speed of sound was just to take the transverse average speed and put it there. Now that's really inconsistent. In fact, although it's true that the transverse dependence of the mode amplitude is rather weak, it's multiplied by a coefficient in the wave equation that's big compared to the angular derivative term. In fact, big enough so that both terms have equal importance in that wave equation. So really, if we want to start with a full wave equation and derive some effective equation, we should sort of integrate the entire equation over the transverse dimension. And that way, instead of computing the transverse average sound speed, we'd be integrating just the transverse average of this quantity, where c is the local speed of sound, and the transverse average of this quantity. Not transverse average, sorry, the transverse integral. Well, r is just a constant. It's the radius of the ring, but there is something that's changing in the transverse direction, which is the transverse area of the ring. Remember, the condensate has a fixed size. In fact, the density goes to 0 at the edge, so the healing length goes to infinity at the edge, and the whole geometric analogy breaks down. But that's happening in a small region around the edge, and so just sort of coarse graining over the healing length scale, we can just say that the condensate has a certain cross-sectional area, transverse area, which I've called A right here. And so when we integrate this equation across the transverse direction, we actually get the radius times the area, which is the volume. And that volume factor also appears here, multiplying the transverse averaged c². And now when we actually evaluate the mode equation, this time derivative hits not the radius, but it hits the volume. So the correct Hubble friction is the time derivative of the volume divided by the volume, not the radius. It's actually perfectly analogous to Hubble friction in cosmology, where you get 3 times the Hubble constant, a factor of 3, because There are 3 dimensions of space. So then to relate this back to the experiment in that 4/7, what we have to understand is how does the volume of a condensate scale with radius as it's expanding? And to understand that, we can use the Thomas Fermi approximation, instantaneous Thomas Fermi approximation. So the idea behind that is that here's the potential as a function of vertical coordinate z and the co-moving radius. This is the radius relative to the central radius of the ring potential. And it has, in this case, we're allowing for arbitrary powers of the radius and the vertical coordinate. And then with some coefficient, some exponential power, n rho and n z. Mu is the chemical potential. And since V is independent of the number of atoms, but mu depends on the number of atoms, the mu dependence that's out in front here in the Thomas Fermi approximation must cancel against mu dependence in the radii. And that way we can find how the radii scale relative to how the chemical potential scales. And so the condensate changes shape and size. The total number of atoms is fixed as it expands, and that determines the scaling of the chemical potential. And therefore, through the argument I just gave, also the scaling of the radii, and therefore the scaling of the volume. And in the end, what one finds is that the v dot over v is r dot over r times a coefficient that's given by these 2 powers as 1/1 plus the reciprocal of the sum of the reciprocals of the 2 powers. And if we put in for the radial power, the 4th power, remember I said the condensate trapping is dominated by the quartic term. And the vertical one, the 2nd power, it's really a harmonic potential. Then we get 1/1 plus a quarter plus a half, and that's exactly 4/7. This is our way of recovering the Gomez-Plata result for the Hubble friction coefficient. Now, this was just a quick and dirty way to get the result. What we've done is a systematic analysis of this problem using the action formalism for the phase perturbation. And we go beyond the thin ring approximation. I didn't say it, but I should have, that the equations I was just showing you, we're simplifying the problem by suppressing the ratio of the thickness of the ring to the radius of the ring. So we go beyond that. We calculate, develop the mode corrections using perturbation theory, taking into account the other transverse modes and quantifying the corrections to the static Thomas Fermi approximation that I just mentioned. Because it's really not a static problem. The ring is accelerating, so there are inertial forces in the co-moving frame that displaces the condensate. And also, it's time dependent, so there's non-adiabatic effects happening. And we look into quantifying the size of those effects to justify why this very simple result of gamma h equals 4/7 worked. So I think that's it. I'll stop there. I don't know if I'm out of time, but it's all I plan to say.
It's perfect timing. Thank you, Ted. And are there any questions from the public?
I have a question. I just seem not to be able to raise my hand.
Yeah, go ahead, Silke.
Okay. Hi, Ted.
Hi.
Just a question. Do you understand, or could you explain to me perhaps the physics behind the phenomenological damping in the system you see? What is, particularly, what is causing this damping in the superfluid? And do you think that the fact that it's a thin ring, is that enhancing the damping?
Oh, I don't think it is. So my understanding of this comes completely from my BEC collaborators who said it's most likely Landau damping, which is, I think, is basically scattering of the phonon against thermal phonons that are present in the condensate. But actually, Ian is here. If he's still here, he could speak to this with more authority than I could, I think.
Ted, I think your answer is perfectly good. The system's undergoing continuous evaporation. So after the expansion, the transverse excitations are being evaporated out. So there's a dissipation channel that allows things like Landau and Belayev damping to convert the phonons to transverse degrees of freedom, and finally short wavelength stuff that can escape.
And this, so am I allowed to ask, there's no hands up, but am I allowed, so this damping to the transverse degrees of freedom, is that enhanced or lowered if you have a strong confinement in the transverse direction?
I would think it's lowered because, you know, you have quantized transverse modes. It takes a certain frequency to excite them.
Are there any other questions?
Thank you.
Thank you. Yes, Zach, go ahead.
Hi, thank you. This is a question for both talks about this experiment, actually. In the first talk, you mentioned that you were not able to see any signatures of horizon crossing or freezing. And then in this talk, you mentioned these corrections. So I was wondering if you had predictions for the horizon crossing that you ought to have seen given your mathematical model, and if these predictions were improved and gave you a better idea of why you didn't see this mode freezing or horizon crossing in the actual system.
So are you referring to the, so I didn't hear the talk by Ian, that might be what you're referring to, but are you asking, by horizon crossing, do you mean basically freezing of the oscillation because of the expansion is too fast? Yeah, and my impression is that in this situation, there's just not, the expansion rate isn't high enough to stop the oscillation. As you just saw in the plot I showed of the mode amplitude as a function of time, the amplitude is changed, and the frequency is changed, but it doesn't go to zero. So I think it's just not a mode freezing type expansion. It's not sufficiently fast. That's my understanding. Maybe Ian, do you have a comment?
No, I don't have an additional comment for that one.
Okay, so let's thank Ted